Welcome to the Hamdans, bridging two worlds, education, tech, and engineering. And the boss, Daisy, AI or nature walks. Join the journey and subscribe.
Look at the text and image on this slide. It asks a simple question. What was the first heating system? For thousands of years, our only defense against freezing temperatures was to burn fuel directly in the middle of a room. As the diagram shows, an open fire radiates heat, but ruins air quality and pulls heated air into the flames. Adding a chimney clears the smoke, but thermal efficiency is only 10%. Most energy goes straight up the roof. Achieving reliable thermal comfort depends on precise management of heat transfer mechanisms and air quality, a goal that raw combustion cannot reach on its own. Today, modern building systems face a massive two-front challenge. We have to provide healthy, comfortable indoor spaces for billions of people while reducing the carbon intensity of the entire built environment. To understand the physics required to solve this, we can look at this photograph of a dog. She perfectly optimized her microenvironment for maximum coziness. Analyzing her setup reveals the same thermodynamic boundary strategies that architects use to design ultra-efficient, low-energy buildings. Building energy design begins with internal gains. Most rooms are not empty. They are occupied by heat-generating sources like people, lighting systems, and electronics. This animated diagram illustrates that concept biologically. Even at rest, a dog's metabolism acts as a continuous furnace, radiating thermal energy into the surrounding air. Without a barrier to trap this energy, convection currents sweep this metabolic heat away, losing it to the environment. Applying a physical barrier stops this rapid loss. In building science, this is the exterior envelope. For our dog, it's a heavy knit sweater. Engineers measure the resistance of this envelope using an R value. A high R value means the barrier is highly effective at keeping internal gains trapped near the source. A highly resistive envelope is the essential first layer for isolating a comfortable microclimate from external weather extremes. Now look at the material immediately surrounding her, the heavy, plush bed. In this cross-section, you can see thermal mass at work. Heavy, dense materials in a room act like a thermal battery, absorbing excess heat rather than letting the room's air temperature spike. Notice how the graph overlays a jagged peak of energy generation. The bed absorbs that energy, creating a time lag. It delays the heat transfer and flattens that sharp temperature spike into a smooth, gentle curve. If the ambient room temperature drops, the decrement factor takes over. The stored energy particles slowly migrate out of the mass, releasing warmth back to the dog. By utilizing heavy materials to capture and slowly release energy, you create a self-regulating environment that stabilizes comfort without requiring constant mechanical intervention. We have now built 3 distinct layers, maximizing internal gains, trapping heat with insulation, and stabilizing the temperature with thermal mass. When architects successfully balance these passive boundaries, the building's structure does the thermodynamic work, significantly reducing the total heating and cooling loads. Minimizing these thermal loads shrinks the size and cost of the mechanical systems required, providing a practical path toward total building electrification and energy conservation. Passive design excels at capturing and retaining heat, but insulation and concrete cannot actively cool a space below the ambient temperature, which is a major problem for preserving food. The Clausius statement of thermodynamics dictates that heat will never naturally flow from a cold object to a hot room. Moving heat against its natural gradient requires external mechanical work. This vapor compression cycle starts in the evaporator, absorbing heat from cold food. The compressor mechanically squeezes the gas, drastically increasing pressure and temperature. Hotter than kitchen air, it flows into the condenser, dumping heat outside before passing through an expansion valve to restart the loop. While passive layers keep us cozy, active mechanical cooling gives us the ultimate control over our environment and our food supply.